So last time we had seen the Cauchy-Frobenius lemma, which says we have a group G acting on a set omega. F of G is the number of fixed point of an element G. So F of G is, well, is the number of alpha in omega, such which are fixed by G. Okay, and we had seen that if you average over G, so you sum over G, and then divide by the order of G, if you average the number of fixed points, what you get is the number of orbits. Now, this number of fixed points is nothing else than the value of the permutation character, okay? Because I mean, these are exactly the ones on the diagonal order matrix of the permutation representations. I mean, a one on the diagonal meaning a fixed point for G. So if you rewrite this as the conjugate of one, this is the trivial character, the character that takes always the value one on all elements of G. We find that this is nothing else but the inner product of the trivial character with chi, with the permutation character. Same thing as saying number of fixed points. So if you take this inner product, you find the number of orbits of G on omega. And what does this mean? If you take an irreducible character, remember this is the trivial character, so it's a linear character, linear meaning that its value on one is one. Of course, its value is one on everything. So that this is an irreducible character. And if you take the inner product with an arbitrary character, you find the number of times this character appears in the decomposition of chi, or the character chi, as the sum of irreducible characters. This is something we had seen here. You write rho as sum of irreducible representations. You write chi as this linear combination with integers and I of distinct irreducible characters, and the irreducible, the orthogonality relations tells you that to know what's ni, you take the inner product of chi I with chi, okay? If this is the character. Because all inner products disappear except for chi I, which is one, okay? So in particular, there's an important, so the number of orbits is this inner product. So this means that chi contains k times the trivial character and then other irreducible characters distinct from one. In particular, G is transitive, meaning that there is only one orbit, that elements of G take, you take an arbitrary element of omega, and the elements of G take it to all elements of omega. This is transitive exactly when this inner product is one, meaning that chi is the sum of the trivial character, which appears only once, okay, because k is one, the number of orbits, and then psi, which is not necessarily an irreducible character, but a sum of irreducible character, but not containing one, because we had already seen that one appears only once, okay? Because it's k, tells you how many times the trivial character appears as a constituent, writing chi as a sum of irreducible characters. And so if chi is the number of orbits is one, this appears only once, and it does not appear here, okay? So one consequence of this is that this inner product is zero, because in psi, you don't have any copies of the trivial character as a constituent, okay? Good. Yes, this is what I was writing here, okay? So chi is 1 plus psi, and 1 psi is 0. This will be important. 1 is not a constituent of psi. Now, what I want to show is the equivalence between these two concepts. The psi is irreducible. In general, psi won't be irreducible. But if and only if the action of G on omega is too transitive. What does it mean to be too transitive? Well, transitive is a particular case, is one transitive, meaning that you can take any element to any other element. Two transitive means that you can take any two distinct elements, okay, to any other this pair of distinct elements, okay? So given distinct elements alpha and beta and distinct elements gamma and delta, there is a G in G which takes alpha to gamma and beta to delta, okay? They have to be distinct. I mean, you cannot take the same here and pretend that alpha goes to two different elements. And well, let's start from here. Okay, so Sn is actually, let's say, n-transitive, which means that you can take any n distinct elements to arbitrary n distinct elements. And the reason is simply that if you take 1 to n, okay, then you take an arbitrary permutation, okay? And remember, this is a not so common notation for permutation, means that I is sent to AI. Of course, you can take arbitrary AI, provided they are distinct, and sigma will take 1n to A1 AN, okay? So as n is actually n-transitive, meaning that any n elements, say for instance 1n, can be taken to any n distinct elements can be taken to any n distinct elements. Okay, so in particular, if n is greater than or equal to 2, then Sn is 2 transitive. As to An, well, okay, let's state it. An is n2 transitive, n minus 2 transitive. And the reason is the following, that okay, no, well, let's put it like this. Well, of course, n has to be big enough that this makes sense. Because, I mean, take a permutation takes 1 to A1, 2 to A2, where all these elements are distinct, and up to AN, and up to n minus 2 being sent to AN minus 2, okay? So far, I have a permutation which takes these elements to these elements here. But then there are two ways of completing this permutation. One is writing, let's say if this is left out, no, okay, let me think for a second. Okay, if this has left out two elements, let's call B and C, okay, then there are only two possibilities. Either you send n minus 1 to B and n to C, or you take n minus 1 to C and this to B. If you choose, so forget this for a moment, consider this permutation here, the one that takes 1 to A1, 2 to A2, n minus 2 to n minus 2, and then this here, okay? If you consider sigma BC, okay, what will this permutation do? Well, this permutation does exactly the same thing to these elements, but then so first you apply sigma, and then you apply the two-cycle BC. So sigma takes n minus 1 to B, but then this takes B to C, okay? So sigma takes n to C, but then this takes C to B, okay? So what you found, you have sigma, you have these two permutations, let's call it tau, okay? Sigma BC equals tau, okay? So if one of these is even, then the other is odd. So only one of sigma tau is even. Exactly one. So you can take 1 n minus 2 to a n minus 2, but then you don't have a choice for the last two elements, because either you take them to be C and you get sigma, but if sigma is odd, is not even, then you have to take tau, which is even, okay? If sigma is odd, then tau is even. If tau is, I mean, if sigma is even, okay, you have found a way of bringing this n minus 2 element to this. But if sigma is odd, you have to take tau, which is even, because you multiply by a 2 cycle, okay? So you can only be sure to take n minus 2 elements where you want, okay? In particular, this means that an is 2 transitive if n minus 2 is n is greater than or equal to 4. To 4, okay? Good. But we are only interested in 2 transitivity, okay? And see in a second. And the reason is the following, that, well, suppose that, for simplicity, that G acts transitively, so one orbit on the set omega, okay? Then G acts naturally on omega times omega. How? Well, it's rather easy. If you have a pair here in omega times omega, how does an element G of G act? Well, it acts separately. Okay? Good. So, so in practice, you have a square, okay, where both the rows and the columns are labeled by the elements of omega. And note that if G acts transitively, then one orbit of the action of G on omega times omega is given by the elements alpha alpha, okay? Simply because since G is transitive, alpha alpha G will be alpha G, okay? And if this is transitive, this is an arbitrary element on the diagonal, say, okay? Because you can take alpha to anything, okay? An arbitrary elements on the diagonal. So this is one orbit, okay? And then what are the remaining elements? The remaining elements are the elements outside the diagonal, the elements on the outside the diagonal. Of omega times omega are of the form alpha beta with alpha different from beta, okay? Of course, because the diagonal is given by the elements in which the two components are the same. Well, they form exactly one orbit. They form in one orbit exactly when G acts too transitively on omega, okay? And this element and these remaining elements form one orbit exactly when G is too transitive. Why? Okay, no, this is really impossible, particularly difficult to read, say. Why is it so? Well, simply because if you have alpha beta with alpha different from beta, so an element of the diagonal, and if another element of the diagonal, gamma, different from delta, so alpha beta is moved to gamma delta by an element G, okay? If and only if alpha G is gamma and beta G is delta. And you can do this exactly when when the group G is too transitive, okay? So you can take a pair of distinct elements to another arbitrary pair of distinct elements precisely when G is too transitive, okay? Good. So suppose, well, okay, so G is two transitive on omega. If and only if G has exactly two orbits on omega times omega. But now, of course, our question is, I mean, we know that the number of orbits can be read from the character. And so we ask ourselves, what is the character of the action of G on omega times omega? Okay. Well, we have to count the number of fixed points. Okay. And so we know that if alpha omega, alpha beta is an element in omega times omega, then and G is in G, then alpha beta is fixed by G, okay? So alpha beta is fixed, is a fixed point, is fixed by the element G, little g. You see, if and only if, since the action on pairs is simply the action on the two components, if and only if alpha and beta are fixed by G. So how many elements of omega times omega are fixed an element G in G, okay? How many elements of omega times omega are fixed by G? Well, you need to take all pairs in which both elements are fixed by G, okay? Because you need alpha to the G to be alpha and beta to the G to be beta. So what is the character? Okay, let's go to the next page. So the number of fixed points of G in G on omega times omega, okay, is given by, well, let's go back to the previous page. So a pair is fixed by G if both the first component and the second component is fixed by G. So how do you build the pairs with this property? You take alpha to be a fixed point of G and beta to be a fixed point of G. So how many of these pairs you have? Number of fixed point of G times number of fixed point of G. Okay, because you can choose alpha arbitrarily in the set of fixed points of G, and the same with beta. So what you obtain, no, next, yes, is given by Fg squared, okay, where Fg, recall, is the number of alpha in omega such that, which are fixed by alpha, by G, okay? But this is exactly chi of G squared, where chi is the character, okay? So where chi is the character of the permutation representation of G on omega. Good. So recall, we had that G is two transitive on omega. On omega, if and only if G has two orbits on omega times omega. But now we use the Cauchy-Frobenius lemma, which tells us that this number 2 of orbits, okay, comes out as the inner product of the trivial character. This is, as usual, the trivial character, with the character of the permutation representation of G on omega times omega. And this is exactly as we saw, chi G squared. Okay, this is the character of the permutation representation of G on omega times omega, okay? We just counted, because the character permutation representation is particularly easy. It's the number of fixed points, okay? And in this case, it's pair of fixed points. So what's this? So this is this scalar product. Well, I just wrote chi of G squared because, of course, 1, if you wish, there's a 1. But there's a more entertaining way of writing this, because I can write this in the following way. I can split the square in 2, okay? Let me write it first as chi G. Well, there's, of course, there's a square. But note that this, of course, is an integer, actually a positive integer. Well, say a non-negative integer, because the number of fixed points, okay? This is a natural number, okay, actually. So let's continue here. This is the same thing as chi G conjugate. I mean, this is an integer. So the conjugate of an integer, of course, is itself. And what's this? This is nothing else than the scalar product of chi with itself. Okay? So let's see. G is to transitive of omega, if and only if G has 2 orbits on omega times omega, if and only if the inner product of chi with itself is 2. Okay? But this is important. Let's go. So we have found that G is 2 transitive on omega, if and only if chi is 2. Okay? Remember, the intermediate step is because this is telling you that the number of orbits of G on pairs, on omega times omega, on pairs of element of omega is exactly 2, the diagonal and everything of the diagonal. But recall that chi is 1, because by assumption, since G is transitive, okay, we have that chi is equal to 1 plus psi, where 1, the trivial character, does not appear in psi, is not a constituent, with 1 psi equals to 0, okay? And then we know that this is 2. Okay, so this is 1 plus psi, 1 plus psi. This inner product is distributive. And these two are 0, okay? Well, this is 0, and then also the other is 0 by obvious, because the other is just a conjugate of this. So this is 0, and this is 0, okay? And of course, the trivial character is irreducible. A linear character is always irreducible, meaning that this is 1, okay? Because a character is irreducible if and only if the inner product of the character with itself is 1. What did we get? That G is 2 transitive, if and only if, you see, 2 is 1 plus psi. So G is 2 transitive, if and only if chi is equal to 1 plus psi with psi reducible. Let's use this thing. Okay, so this means psi is an irreducible character. The symbol here G is common, is an irreducible character of G. And why is it so? Because you have 2 plus 2 equal 1 plus something. So this if and only if psi is 1. And this is only if and only if psi is irreducible. I mean, this the orthogonality relations tell you that the character is irreducible if and only if the inner product with itself is 1. Okay, and here we obtain that this is 1. Okay, so this is important. G is 2 transitive on omega if and only if chi is 1 plus psi, where psi is also irreducible. This is a trivial character which is always irreducible. How do we use this recipe? Well, the recipe is that once we have a G acting too transitively on a set, you can subtract one and you obtain an irreducible character. We'll find immediately an example. You'll be bored with S3 by now, but we'll soon move to a couple of other groups. So consider S3. We know already what the character table of S3 is, but consider this acting naturally on omega equal 1, 2, 3. Okay. So what is the permutation character? Of this action? We had already calculated this, but let's do it again. So we write the conjugacy classes, the conjugacy class of 1, the conjugacy class of 1, 2, 3, and the conjugacy class of 1, 2. And here you have to write the permutation character, which remember is just the number of fixed points. Okay, we write chi because characters ch is the chi in Greek, but it's nothing else than the number of fixed points. So 1, of course, fixes 3 points. Okay, 1, 2, 3 fixes nothing, and 1, 2 fixes exactly 1 point, 3. Okay, so number of fixed points. And now you know that chi of G equal 1 of G plus psi of G, say where psi is irreducible. Because S3 is too transitive. I mean, from S2 onwards, they are always too transitive, as S3 acts too transitively on omega. Okay? And so this means that what's psi of G? Psi of G is chi of G minus 1, okay? The values. So what we had, yes, but except that I should have moved. Let me see whether I'm able to do this, because I should really start doing this. Okay, yes, I made space. Okay, I'm learning. So what do we do here? No, but this is not what I wanted to do. No, come on. Redo, and then this. So what's psi, the character psi, okay? You obtain the character psi subtracting 1 from all the values of chi, because this is the trivial character. So it has always values 1. So you subtract it, you find 3 minus 1 is 2, 0 minus 1 is minus 1, 1 minus 1 is 0. And this is the third character, besides the linear character of S3 that we already knew about. Okay, so this character, we had seen this character coming out of countless many, in countless many ways, but one of the ways is this. It consists in taking this permutation character, okay, and in subtracting 1, okay, and finding that this holds. So in other words, the trivial character is 1, 1, 1 of the 3 conjugacy classes. The character psi is 2 minus 1, 0, and the character chi is the sum, 3, 0, 1, okay? This is another way of putting it. I computed psi as the difference, but of course, here is the sum. So chi is sum of the trivial character and an irreducible character. There you go, okay? And this trick is particularly useful with the alternating and symmetric groups. So we'll now compute compute the character table of A4, okay? Good. So A4, well, yes, we'll see that in a second. So first of all, linear characters. So recall that you obtain the linear characters, they correspond to the characters, to the linear characters of the group A4 over A4 prime, where this is the derived subgroup. This is something we had seen in the first part of the course when we were discussing soluble groups, that since linear characters have an image which is abelian because it's a subgroup of C star of the multiplicative group of the complex numbers, they have the derived subgroup in the kernel. So they are really morphisms from this quotient to C star. So what's this quotient? Well, let me think for a second. Yes, okay. Perhaps let's discuss this structure detail of A4, okay? We will remind us, we'll recall the conjugacy class of A4 in a second, but first note this. A4 has a subgroup made of all elements of order dividing 1 or dividing 2. Because, well, okay, let's, because the elements of A4, what can you, well, you have the identity, okay? These are the even permutation of 4 elements. Then you have the product of two cycles, okay? Because this is an even permutation, a product of two cycles. Then you have things like 1, 2, 3, which are the product of also of two cycles, because this is 1, 2, 1, 3, okay? And the other elements are odd, okay? Because what you leave out, no, okay. Sorry, there's no space here because just a second. Okay, because you have 1, 2, but this is not okay because of course it's odd. And then you're also left with 1, 2, 3, 4, but this is the product of 3 2 cycles, so it's also odd, okay? So you have these elements here. How many of these elements here, of this element 1, 2, 3, 4 you have? Well, let's write them. Well, first I write 1, okay, then 1, 2, 3, 4. Essentially, you choose the first 2 and the other follow. Sorry, there's no comma here. Okay, and there are no others because I mean you choose the first 2 cycles, 1, 2, 1, 3, 1, 4, and the other is forced, and then you see that you have no other choices because since this is a product of two cycles, 1 has to appear somewhere, and so I have chosen all the possibilities: 1, 2, 1, 3, and 1, 4. So there are no other elements. This is a subset of order 4, but we know by zero theory, since A4 as order 12, which is 2 squared times 3, that there has to be a subgroup of order 4. Since a subgroup of order 4, in a subgroup of order 4, all elements have order dividing 4. And here, I mean, these elements have order dividing 3, these are elements 2, of course. There are no other elements that could go in that have order dividing 4. So this has to be a subgroup, okay? Because it has to be the unique CILO2 subgroup of A4. So this is the unique CILO2 subgroups, 2 subgroup of A4. And this is usually called V or V4, the Klein-Ferer group. The group of order 4 which is not cyclic. So recall the argument. I mean, we know from zero theory that there has to be at least one subgroup of order 4, and the elements of this subgroup have order dividing 4. but I mean, all these elements have already divided in three. So only these elements are left to make at least one CO2 subgroup. Since there are exactly 4 elements like this, these are order 1, which divides 4. These have order 2, which divides 4. This has to be the unique CO2 subgroup A4, okay? So of course you can verify that the product of 2 elements is the third one, but since Sylow theorem tells us that there is at least such a subgroup, here you have only 4 elements to make such a subgroup, so this has to be the CO2 subgroup, okay? Since it's unique, this is normal in A4, okay? Good, because remember, CO2 subgroups form all the CO2 subgroup of A4 form a single conjugacy class. And so if there is only one, it has to be normal, a conjugacy class made exactly of one subgroup. Then, if you consider the quotient, okay, since this is order 12 and this is order 4, the quotient has order 3. So the quotient is cyclic of order 3. That's abelian. Okay? So remember, since this quotient is abelian, the results we saw when discussing the soluble groups tell us that the derived subgroup is contained in V because the derived subgroup is the smallest normal subgroup whose quotient is abelian. Since this quotient is abelian, A4, the derived subgroup has to be contained in V. And this is, of course, is different from 1 because it's easy to see that the group is not abelian. As A4 is not abelian. Easy to see. I mean, you take a product of 2 elements. Well, for instance, 1, 2, 3, 4, and 1, 2, 3, and see that they don't commute. But the point is that actually the derived subgroup is V. Why is it so? Because A4 prime is V, because so we recall also a concept from the abelian from the part of soluble groups, because because V is a minimal normal subgroup. So recall, we have just seen that A4 prime is a subgroup of V which is greater than 1. So, and of course, this is normal in A4. Actually, the derived subgroup is characteristic, well, but it's normal. Minimal normal subgroup means that there are non-proper normal subgroups in V different from 1. So if it's a minimal normal subgroup, this implies that A4 prime cannot be properly contained between 1 and V. And the reason why this is minimal is simply because the 3 non-trivial elements of V are conjugates. So if you conjugate this with 1, 2, 3, what do you find? Well, 1 goes to 2 and 2 goes to 3. So 1, 2 goes to 2, 3. And then you see immediately the 3, 4 goes to 4, 1. 3, 4. Sorry, 1, 4. Because 3 goes to 1 and so on. And then if you do 2, 3, 1, 4, and you conjugate again with 1, 2, 3, what do you find? 2, 3 goes in 3, 1, let's say 1, 3, and 1, 4 goes in 2, 4. Okay, so you see that if there is one element, then there are all the other elements. Let's just compute the other conjugate, and you'll see that it's 1, 2, 3, 4. So if you have a normal subgroup containing V, if it contains one element, you conjugate, you find it contains all of them. So it's a minimal normal subgroup. Okay, so the derived subgroup is in fact V. Okay, good. So this means that the linear, as I was saying, that the linear characters of A4 are the linear characters correspond to the linear characters of A4 over V, which is recalled the derived subgroup. So now we start constructing the character table. Okay, so the character table of A4. Okay, so we have first to find the conjugacy classes. Well, I could have started with S4. Well, of course, there's the identity. And of course, there is 1, 2, 3, 4. And we just saw this calculation here, that there is a unique conjugacy classes of all these elements, okay? And then there is the conjugacy class of 1, 2, 3. But you see, okay, you see what's the size of the conjugate class of 1, 2, 3, okay? Well, it's orbit stabilizer, okay? So the order of A4, which is 12, has to be the order of the conjugacy class, all conjugates, times the stabilizer. And recall, so this orbit, and here's the stabilizer, and the stabilizer in the conjugacy action okay, so this is the centralizer, is the centralizer of 1, 2, 3, okay? Okay, so orbit stabilizer tells you that the order of the group is equal to the order of the orbit of 1, 2, 3 under the conjugacy action of A4 times the centralizer. This centralizer, of course, has 3 elements, at least 3 elements, say, but it's actually this one. It cannot be larger because you remember that we had seen in the Theoria dei Gruppi course that A4 has no subgroup of order 6. So the centralizer, of course, contains the powers of 1, 2, 3 because they commute with 1, 2, 3. So as order at least 3. It could have order 6 or 12. It cannot have orders 12 because having order 12 means that the centralizer is the whole group. There is 1, 2, 3 commutes with all elements, but we have just seen that it does not commute with these. And then there is no subgroup of order 6, so it cannot be a group of order 6. So this is order 3. Okay, and so this is order 3. And so this means that this orbit has 4 elements because 12 is 3 times 4, okay? And now you see how many elements of this form are there? There are exactly 8 elements because remember the formula. How do you count elements of the form 1, 2, 3? So the first element, you have 4 possibilities for the first one, 3 elements for the second one, 2 elements for the third one, and then you divide by 3 because 1, 2, 3 you can write as 2, 3, 1, and also 3, 1, 2. There are 3 ways of writing this. So there are 8 elements. But we found that the orbit of this has 4 elements. So 4 elements here, these are 3, this is 1, this number of elements. And then it's easy to see that there is another class. There has to be another class, which is the class of 1, 3, 2. If you want, perhaps you remember from the Theoria dei Gruppi course that the class of an element in S4 splits in two in say in a sense, splits in two in a n, if and only if the centralizer contains only elements, even elements. And this is exactly the case, okay? The centralizer of 1, 2, 3 contains only even elements. And so the class of 1, 2, 3, which is a unique class, as we will see when we talk about S4, a unique class in S4 splits in two here. But we have computed the centralizer and see what happens, okay? Fine. So there are 4 classes, and so there have to be 4 characters. And we know that 3 characters will be the linear ones. Why? Because these are the characters of A4 over V, which has order 3, okay? So linear characters, there are 3. Linear means that the value on 1 is 1. They are the characters of the quotient A4 over V. So this means that this is in the kernel, okay? And then we have the characters of a group of, I recall this in a second, of a group of order 3. And remember, the character of a group of order 3 are the trivial character is always there, and then omega, omega square, and omega square, omega, where omega is a primitive third root of unity. So you see, you first compute, say, the characters of the group generated by 1, 2, 3, okay? And then note that, the characters, the linear characters of A4 are the characters of the quotient A4 over V, so V is in the kernel, okay? Because the idea is that, this is cyclic of order 3, okay? So you have a linear character. And then, of course, you put the natural epimorphisms here, and you obtain linear characters of A4, where V goes in the kernel here, okay? So this is how you do the linear characters. You put this in the kernel, and then you get the values we already know for a group of cyclic group of order 3, okay? Like this. Good. So there are 4 conjugacy classes. There is 1 character to go still. And what's this character? Well, we know already something, because we know that these are the degrees of the characters. Okay, let's call chi. No, well, not chi, we'll call it psi. You know that the sum of the degrees of the reducible characters has to be the order of the group. So these characters are linear. So the formula is the order of A4 is 12. And this is 1 square plus 1 square plus 1 square. So these are the linear characters, plus psi of 1 square, okay? Because this is the formula. You take all the reducible characters. If you do sum the squares of their degrees, which means their values in 1, you obtain the order of the group. So this is 3, this is 4. No, sorry, no, come on. This is 9, okay? And so this means that psi of 1 has to be 3, okay? So a character of degree 3, okay? But how do you compute psi? Well, it's very easy, because A4 is 2 transitive on omega equals 1, 2, 3, 4. Okay, because remember that an is n minus 2 transitive. So since n is 4 here, n minus 2 is 2, so it's 2 transitive. So what's the permutation character? Of A4 acting on omega? Well, we call it chi. Here we write the conjugacy classes. Okay, so the values are the numbers of fixed point, okay? So remember, chi g is the number of fixed points. So 1 fixed 4 points. 1, 2, 3, 4 fixed 0 points, okay? And this fixed 1 point, okay? And so remember that if you take psi, which is chi minus 1, you subtract the trivial character, you get an irreducible character. Why? Because it's too transitive, okay? So you subtract 1, 3, minus 1, 0, 0, okay? And this is the missing character. Know that we have lots of information here. So for instance, why are these two 0? Because remember that if you multiply a character by a linear character, an irreducible character by a linear character, I'll write this down, you obtain another irreducible character, okay? So let's write this on the next page. Remember, well, come on. If psi is an irreducible character, and lambda is a linear character, then psi lambda, whose definition we will recall soon, is again is irreducible. So if we look at the missing character here, because I mean, we wrote it down, but what we knew is that it has to be a character of degree 3, okay? So suppose we don't know exactly, so we know that this character is 3ABC, okay? Where this is 1, this is 1, 2, 3, 4, the values on the conjugacy classes, okay? So this is the missing character, okay? But then you know that if you multiply it by a linear character, then you obtain again an irreducible character. So we'll take any of these two characters, or these two linear characters. I mean, of course, if you multiply by the trivial character, you get the same character. No information here. But if you multiply by this, okay, you obtain that, let's say, the product 3a omega b omega square c. This is, again, another irreducible character. But we know already from the table that there are only 4 irreducible characters. 3 are linear and 1 is degree 3. So we found another irreducible character of degree 3, okay? But it has to be exactly the same character we already had. So this has to be psi, okay? So this means that b equals omega b, but omega is different from 1, so this means that b is 0. And similarly, c equals omega square c, and again, since omega square is different from 1, it means c is 0. So we see the reason why b and c are 0. The reason they are 0 is that in this table, this character remains irreducible if you multiply by this character here. And so, since there is exactly one character of degree 3, and 3 times 1 is 3, these two values have to be 0. Whereas here we are multiplying by 1, so nothing happens, okay? And note, once you know that this is 3 something 0, 0, you can obtain, well, let's do this. So, just to clarify, I've computed this character with this trick of two transitivity, okay? But another way of calculating this character would have been first to note that if the character is 3 ABC, 3 we know already, then B and C has to be 0 because of this property. And then once you know that psi is 3A 0, 0, then this time you take the trivial character, okay? And since these are two distinct irreducible characters, you know that this is 0, okay? The inner product, because these are two irreducible distinct characters. And what's this character? Well, we write the number of elements in the conjugacy class here. This is 1, this is 3. So this is 1 over 12, okay? But this is, of course, irrelevant because the result is 0. 3 times 1, plus 3 times 1 plus 1 times A, okay? So what we get that, forget about the 1 over 12, 3 plus 3A is 0. So A is minus 1. So we found exactly what the value has to be minus 1. So you see all the stuff we have done, we have studied, so in particular, the irreducible, the orthogonality relations, provide redundant information on the character tables. I mean, we have computed psi as the character coming from the two transitivity, but we could have computed it in this other way that we have seen. We could also see what the associated representation is, but let's proceed with S4, and then perhaps we do it with S4. Okay, so now we do S4, okay? S4 is in a certain sense easier. Why? Because, let's see. Well, first of all, we want to go into the details, but it's always true that the derived subgroup of S4 is A4, okay? And then conjugacy classes are easier because conjugacy classes correspond to what was the name? The shapes of the elements. Well, okay, shapes of the elements. Well, there has to be a better name. What I mean by that? So let's build this character table. Okay, so so partitions. Okay, partitions of 4. So you have the identity. Okay, and then you take an elemental shape, a 2-cycle, and these are a single conjugacy class. Remember that elements of the same shape, so all 2 cycles are conjugate. And then you have, let me think for a second. No, but I'm not doing things in the right order. So for some reasons that will become apparent later, I prefer to write first 1, 2, 3, 4, okay? And then I write 1, 2, 3, and then I write 1, 2, and then I write 1, 2, 3, 4. And the point is, these are the conjugacy classes. I mean, all elements of this shape are conjugate because the shape is a product of two disjoint 2 cycles. All elements of this type are conjugate. All elements of this kind are conjugate. Same with this. How many elements? So number of elements. Okay, this is the element, number of elements, 1. And then there are formulas, you know, for instance, how many elements of this shape you have. Well, you have to fill these products of 2 cycles. So 4 elements here, then 3, 2, 1. And you divide the first by 2 twice because you can exchange the elements here, and then once more by 2 because you can exchange the 2 cycles. So this is 3. How many elements here? 4 times 3 times 2 times 1 divided by 3. So you have 8 as before, except that in A4, you had 8 elements, but split in 2 conjugacy classes, whereas here you have just 1 class. And here you have 4 times 3 divided by 2, 6. And here you have 4 times 3 times 2 times 1 divided by 4, because you can write a 4 cycle in 4 different ways. And that's 6, okay? So we know that we have 5 irreducible characters, because the number of irreducible characters is the same as the number of conjugacy classes. Let's first consider the linear characters. Since the derived subgroup of S4 is A4, and the order of S4 over A4 is 2, you have exactly 2 irreducible linear characters, okay, linear ones. So 1 is the trivial characters, that's the easy part. And then you have the other character of a cyclic group of order 2, which means that all these are in A4, so these are in the kernel, okay? These are the elements we find before, and all the elements not in the kernel, it takes value -1, okay? So if you have a cyclic group of order 2, the non-trivial linear character takes the element different from 1 to -1, okay? Roots of unity, second root of unity. And these are in the kernel in A4, we saw before, and these are not in the kernel because these are odd elements, and so the value here is -1, okay? What can you say of the three missing characters? Well, let's take a little break and then we'll come back. What do you mean taking a break? There is a result that I could have used from S4, but remember this argument from Teoria dei Gruppi, that if you have G, the group G acting on a set omega, okay, and alpha an element of omega, and H a subgroup of G, which acts transitively on omega. So of course, if H subgroup G acts transitively, just one orbit, then also G acts transitively because the elements of H are enough. And then this result, which goes sometimes under the name of Frattini argument, tells you that G is the product of two subgroups, and these two subgroups are G alpha, the stabilizer, times H. Okay, this stabilizer of alpha in G. Let's recall the proof because it's very short and simple. Because you take any G in G, okay, and then you take alpha to the G. So you let G act on alpha, the fixed element. Now H is transitive, which means then there is an A element H which takes this back to alpha, okay, as H is transitive. So H transitive means that if you take any two elements of omega, there is an element of H take the first element to the second element. My two elements here are alpha to the G and alpha. So there is an element H in H, which takes alpha to the G to alpha. Then, of course, by the first axiom of group actions, this is alpha to the GH. And here I have that alpha to the GH is alpha. So GH is in G alpha. And so this means that G is in G alpha H inverse, which is, of course, an element, which is a subset, it's a coset, really, but it's a subset, of course, of G alpha H. Okay? So what we have found that if you take any element G in G, is an element of G alpha H. And of course, this means that G alpha H, the product, is the whole of G. Okay? So group, transitive subgroup, then you can split G as the product of the 1-point stabilizer of alpha times H. You apply this to S4, S4, so G is, well, let's write it as it should be written. Apply this to. Of course, I have to tell you G acting on omega and so on. So G is S4. Omega, surprise, surprise, is 1, 2, 3, 4. Okay. Alpha is 4. Okay. And H is what we called V. I could have done this argument also with A4. It's this subgroup here. Which is, of course, transitive because, well, it's written horribly, because you see that this group takes 1 everywhere, because this takes 1 to 1, this takes 1 to 2, this takes 1 to 3, and this takes 1 to 4. So this is transitive. And so what we get is that G is equal to H here. What's the stabilizer? Well, the stabilizer of 4, okay, this horrible, this notation. The stabilizer of 4 in S4 is nothing else but S3, because it is given by all permutations in which, remember that if an element is fixed, we don't write it in a permutation. So if 4 is fixed, you have permutations on 4 elements in which 4 does not appear. So these are just a permutation of 1, 2, 3, okay? So you have S3 here, okay? Because S3, of course, is a subgroup of S4, okay? Because of this convention that if you take the element 1, 2, 3, this is an element of S4 fixed in 4, okay? And okay, and remember that this, since, okay, fine, just let's do it like, so S4 is equal S3, the product, where H is what was called V in the previous, in A4, okay? And of course, S3 intersect H is trivial, okay? Why is it so? Well, of course, because S3 is the stabilizer of 4, and the only element in H stabilizing 4 is 1, okay? And by the same argument as before, H is normal in S4, okay? Because, I mean, because H, recall, because H consists of 1 and then a conjugacy class. These 3 elements form a conjugacy class. So when you take H to the G, 1 remains where it is, and these 3 elements are permuted among themselves. So H is normal, okay? And then this means that S4 over H, okay, equals S3H over H. And you remember this is the second isomorphism theorem. This is isomorphic to S3. So you simplify H, except there's something left. S3 intersect H. But this is trivial, okay? And so this is isomorphic to S3, okay? So you have S4. This is something that does not happen in the higher symmetric groups, because AN becomes simple when has at least 5. But here, you take the quotient of S4 over H, okay? And it's S3, whose character we know already. And remember that if you have a character, okay, a representation or a character of S3, okay, that is a character of S3, well, yes, which is a function to C, then of course you can compose with the quotient map, because S4 over H is S3, and you obtain a character of S4. Okay, so you simply take, okay, so let's do it like this. So suppose that this is sigma, a character of S3. So you define a character of S4, how? Tau of an element G in S4 will be sigma of GH, okay? So GH is a group isomorphic, so S4 over H is isomorphic to S3, so this is in S4 over H, which is a group isomorphic to S3, okay? So if you have a character of S3, you get a character of S4, which on an element G has the value that sigma S on this coset, which is really an element of S3. Let's see how it works in practice. Okay. So look, this is S3, you see. Okay. So there will be one character, which is, remember, let me write here in a corner, the 2 minus 1 character of S3. Okay. Remember, this is the 2, 1 character. So the idea is the following. You copy this, okay? Because 1, 1, 2, 3, and 1, 2 form S3. So this is what you get. This is in the kernel, okay? Because S4 over H is isomorphic to S3. So this is in the kernel, so the value is 2, is the same value as 1. And this element is not in the kernel because this is odd, okay? Whereas all these elements are even. So one can see that the value is the same value as 1, 2, okay? It has to be, because in the quotient, this element of order 4, so in the quotient, it will have element order divided in 4, and it would have element then 2, okay? Okay, so what we've done here, let's do it again. So no. So these are the values of this character of S3. S4 modulo this H gives you S3. So this is an element of H, so this is in the kernel, so the value will be the same as 1, okay? And this element is not in the kernel, and it's easy to see that in the quotient it goes over 1, 2, an element of order 2. So the value has to be the same of this, okay? So we have seen an instance of, say, lifting a character. We know a character of S3, S4 modulo H is isomorphic to S3, and so from the composing the map from S4 to S3, which you get here, you get a character or a representation, if you prefer, of S4. Okay, and let's see what is missing. There are 2 characters missing because there are 5 conjugacy classes, and so far we have found 3 characters. What can we tell about the other 2 characters? Let's call it Chi1 and Chi2, okay? Well, you know that if you sum the squares of the degrees of the character, you get the order of the group. So let's see what we get. So 24 has to be the sum of the squares of the degrees. Let's get back a second to check. So the degrees so far are 1, 1, 2, and then these 2 degrees are known degrees. So 1 square plus 1 square plus 2 square plus Chi1, 1 square plus Chi2, 1 square. Of course, this is this is 6. So we find that 18 is equal to Chi1, 1 square plus Chi2, 1 squared. And then it's a moment of reflection to see that the only way of obtaining 18 as the sum of 2 squares is to have 3 and 3. Okay, just think for a second. So they have to be 2 characters of degree 3. Okay. Well, one of them will be easy to compute, and it will be the one coming from the permutation representation. Well, okay, I'm tempted to change the name, but it doesn't matter. No, it's okay. So consider the character of the permutation representation, the natural permutation representation of S4 on omega, which is 1, 2, 3, 4. So remember, this is a very easy character because the value on G is the number of fixed points of G. So let's call it chi, okay? This is not ambiguous because the other characters called chi1 or chi2 and chi2. So I'll write the elements here. Okay, so what's the number of fixed points? Well, of course, it's 4 for the identity, which fixes everything. It's 0 for 1, 2, 3, 4. It's 1 for 1, 2, 3, because 4 is fixed. It's 2 for 1, 2. And it's 0 again for 1, 2, 3, 4, which circles this. And then remember, since S4 acts 4 transitively, actually 2 transitively on on omega, say chi minus 1 is an irreducible character. Because chi is equal to 1 plus psi, and this is irreducible, okay? Because, I mean, 1 plus something means that the group acts transitively. If it acts too transitively, then it's 1 plus psi with this irreducible. So what's the psi, which we'll call chi1? You subtract 1, okay? 3 minus 1, 0, 1, minus 1, okay? 3 minus 1, 0, okay, I could copy and paste it, but I'll rewrite it. So I simply taken these values, fixed point, and subtracted 1. And this will be an irreducible character. 0, 1, and minus 1. Okay? So this is one character. How do you find the other? Well, that's this trick we know, that if you multiply an irreducible character by a linear character, so let's call this lambda 1 and this lambda minus 1, so you know that chi1 times lambda minus 1 is again an irreducible character, okay? Because you multiply an irreducible character by a linear character, okay? Not any, I mean, for instance, if you multiply this by this, you get 3 times 2, 6. Of course, there's no irreducible character of degree 6, so this doesn't work. But if you multiply this by a linear character, you get what you want. And so what you get, you take these values and you multiply them by the values of lambda minus 1. So it's minus 1 times 1, 0 times 1, well, not much happening here, 1 times minus 1, and minus 1 times minus 1. Okay, so these are all the irreducible characters. So how do we find them? Well, the two linear characters we got from the quotient S4 over A4. This character we got from the quotient S4 over H or V, which is F3. So this is the lift of this irreducible character of S3. This comes from the permutation representation, and this comes as a product, okay? Chi2 is the product of chi1 times lambda minus 1. Perhaps we could finish this by discussing, let me erase this, because, so this was minus 1, yes. By discussing how can you represent, how can you obtain a representation affording chi1, okay? Let me copy this. Good. Add to, no, let's add to library, and then should be the last one. Okay, yes. It's a bit dirty, but dirty meaning that there are some leftovers. So how about a representation affording this, affording chi1? Let's recall the labels here. This is the identity. This is 1, 2, 3, 4. This is 1, 2, 3. This is 1, 2. And this is 1, 2, 3, 4. Okay, I'll just mention. I won't go in all the details, but we'll see something. Okay, so representation rho affording chi1. Of course, rho of 1 has to be 1, 1, 1. I'm not writing the zeros. Then consider what rho of 1, 2, 3, 4 could be. Okay. Since this has order 2, okay, the eigenvalues is a diagonalizable matrix. Remember the usual stuff with a minimal polynomial, with eigenvalues, which are second roots of unity. Well, of course, it means 1 or minus 1, okay? Because the roots of unity, I mean, roots of s square minus 1 equals 0, okay? So, of course, they have to be 1 or minus 1. We know that the character is minus 1, okay? Since the value of the character you will need to have 2 minus 1 and a 1, because otherwise, if you take 2 ones or something else, you don't get minus 1. You get 2 minus 1s and 1, 1, okay? So, for instance, we can assume, choosing a suitable basis, that this is of the form minus 1, minus 1, 1, okay? Now you see this holds for all the elements in the conjugacy class, okay? So what could 1, 3 to 4 be? Well, okay, there are several things going here. Okay, let's, so H or V is this group here. Is an abelian group. Remember that groups of order p squared is abelian. So this means that the three matrices that you get by applying rho to these three elements can be put in diagonal form, diagonalized at the same time. So there is a basis with respect to which all of three of them are diagonal. So so their image is under rho. Can be diagonalized at the same time. There is a unique basis such that with respect to which all three of them are diagonal. And I mean, since the character has value -1, you need to have 2 -1s and a 1s. It's not possible. I write that something and then I erase it. It's not possible that the 2 ones are exactly in the same place, because otherwise, if you take the product, then you get the identity matrix, which has trace 3 and not -1. And the product of these two elements, 1, 2, 3, 4, and 1, 3, 2, 4, is the third element. So this is not possible, okay? Because otherwise, the third element goes to the identity, and you get a 3 here, which is not right. So you don't know exactly where the ones are, but what's important is that they cannot be in the same place. And then if you check this goes pretty well with this, because if you multiply, you find exactly that you get the 2 -1s in the third possible position. So you see, this fixes this element, this fixes this basis element, and this fixes this basis element. So we got 3 matrices which we give you -1. What's the image of 1, 2, 3? Well, remember that we had seen that 1, 2, 3 conjugates conjugate 1, 2, 3 to let's see, to just a second, 2, 2, 3, 1, 4, to 1, 3, 2, 4, and then back, okay? Conjugates the 3. So of course, the same holds for row 1, 2, 3. okay? Okay, because you simply apply rho, okay? And it's not difficult to say, to see, you see, this is the eigenvector of this with respect to 1. It's a fixed point of this. This is the fixed point of this, and this is the fixed point of this. And since this rho 1, 2, 3 conjugates one to the other, it has to conjugate the three of these spaces one to the other, okay? Okay, let's see this detail, and then I'll skip the rest, which is complicated. So give a name to the basis. Let the basis be V1, V2, V3. Okay. So we see how you build. I won't go into all the details because we have our time is up. So you see, you know that V3 rho 1, 2, 3, 4 is V3, so it's fixed. Okay, let's look here. The third element here is fixed by this. Okay, good. So you know that 1, 2, 3 conjugates this to this. Okay, so you know that, let's write it here. 1, 2, 3, 4 conjugate with 1, 2, 3 is 1, 4, 2, 3. Let's see. Yes, this is correct. Okay, yes, this is correct. So in other words, conjugate, let's write this in painful, all the painful details. This is the conjugate. But then you can move this to the other side. So you have 1, 2, 3, 4. 1, 2, 3 equals 1, 2, 3 times 1, 4, 2, 3. Okay? And of course, if this holds for the elements, it goes also when you apply rho. I'm skipping the double parentheses here. Okay, so look what happens when we apply rho 1, 2, 3 here. Okay, so you have V3 of rho 1, 2, 3, 4. Rho of 1, 2, 3. This V3 rho 1, 2, 3. Okay, but this is the same as let's see whether this is correct. Yes, yes, okay. This is the same as V3 rho 1, 2, 3. Okay, rho 1, 4, 2, 3. Okay, so let's look. So I have computed, I have applied to V3 first this, and then this. And we know that V3, that these elements fixes V3. So we have this. What we have here? We have that V3 rho 1, 2, 3 is an eigenvector for rho 1, 2, 3 with respect to eigenvalue 1. Is fixed, okay? So this means that V3 rho 1, 2, 3, let's see what 1, 4, 2, 3 does. Rho of 1, 2, 3, 4 fixes the first basis element, okay? So this is in the space generated by V1. And then you can see that V1 applied to this has to be in the space generated by V2. So by normalizing as we did earlier in the case of S3, you can see that you can by changing its basis, you will see that V3 goes to V1, goes to V2, and goes to V3. So rho 1, 2, 3 will be this matrix. Let me write it here so you'll see that it's okay. So V3 goes to V1, so there's the one here. V1 goes to V2, so it goes here, and V2 goes to V3, okay? And so you see that there are all zeros on the diagonal, and this fits with the fact that you have 0 here. And then with some other tricks, you can also find what goes on here, because I mean, 1, 2 will be exchanging the minus ones and the like. But we won't go in all details. Suffices to say that we have computed the character table of S4 using a few tricks, okay? It would be possible also to compute the character table of A5 or S5, but this is fairly complicated, and I'll do it if I have time at the end of the course. On the other hand, instead, I mean, next time we will start talking about integrality, which means that one of the advantage characters is that we go from the group to the complex numbers, and then we can exploit properties like being algebraic integers, which we'll recall in the next lecture. Okay, that's all for today. Thank you very much.